Okay, section 9.4, radius of convergence, part 2. In this section, we're going to look at the ratio test. So write this down. Let the sum of a sub n be a series with positive terms. This will be important. And with the limit, as n approaches infinity, of the n plus 1 term divided by the nth term being called L. The series will converge if this limit is less than 1. The series will diverge if this limit is greater than 1, and the test is inconclusive if L equals 1. So this will only work if my ratio test produces a value less than 1 or greater than 1. Take a look at this fraction, a sub n plus 1 over a sub n. It will be very useful for us to write this as a sub n plus 1 times the reciprocal of a sub n. So keep that in mind. Okay, so let's look at the first one. Here's our example. This is the function. We want to use the ratio test to find our radius of convergence. So using the ratio test, this expression is this function when I substitute n plus 1 in place of n. This is my original function as a reciprocal. So this is my a sub n plus 1 times the reciprocal of a sub n. And I'm taking this as the limit as n approaches infinity. So combining as fractions on top of each other, n plus 1 over n, x to the n plus 1 over x to the n gives me x, and 10 to the n over 10 to the n plus 1 gives me over 10. The limit as n approaches infinity, this expression approaches 1, so I'm left with this expression. Remember, if this limit is less than 1, it will converge. We've got an absolute value around this because if you remember, it said we had to have positive terms. So we're going to use absolute convergence to prove convergence. So setting this less than 1, it converges absolutely for negative 10 to 10. Therefore, it will converge. The series diverges if we are outside of this radius or interval of convergence, and the radius of convergence is 10. So that's one quick example of using the ratio test. Okay, let's look at another one. Convergence or divergence, if this is my function, no x is in here, so I don't need to worry about absolute values. Everything will be positive here. So again, the ratio test. Now they've written it as the n plus 1 term over the nth term, then taken the step to multiply by the reciprocal. Again, gathering like terms together, 2 to the n plus 1 over 2 to the n is 2. 3 to the n plus 1 over 3 to the n plus 1 is the denominator. I'm looking for the limit as n approaches infinity. So they have multiplied all of these terms by 3 to the n, then showing as n approaches infinity, these approach 0. So we get 2 over 3, 2 times 1/3, and the series will converge because 2/3 is less than 1. So we have proven convergence because the limit of the ratio of a sub n plus 1 over a sub n is less than 1. Now, I would look at this a different way, get the same answer. As n approaches infinity, these are inconsequential. 3 to the n over 3 to the n plus 1 is the limit as n approaches infinity of 2 times 1/3. Again, I get 2/3 for my answer, and I can prove convergence because that is less than 1. That's it for the notes. Pretty simple. We're going to do a bunch of ratio tests tomorrow. That's it.